Okay, good afternoon to all of you. From the place where we left yesterday, we were talking about the binary search tree. Now, already I've told you yesterday that in a binary search tree, the searching time can be a maximum of order of n. And the best time to search in a binary search tree will be an order of log n to the base 2. But we cannot guarantee that this particular tree will behave in an order of log n times, because it depends on the elements what are being input by the user in the order. Now in that case, if the order is obviously make the tree as a complete binary tree, we will be ending up in getting a order of log n. But in the worst case, if the tree is in the ascending or descending order, or in any other order which will make it a skew tree, the tree will become, the searching time will become an order of n. That means to be very perfect, the complexity of search is order of n. The complexity of search is order of n. Now let us try to find an algorithm that how I am going to insert an element in a binary search tree. Now you already know that when you are going to insert an element, you have only one place to insert. Only one place to insert. While searching, you have to search the corresponding branch which will lead to that element. Now, for example, suppose I have a tree like this. Maybe this is 100, 80. Suppose I have made the tree like this, where their number of elements over here are, say, there are the number of 7 elements, and I am going to make a tree. Now, suppose I want to insert an element. Obviously, to insert, we start, as I told you yesterday, we will start comparing from the root. Now, the only thing what you are having is the root. And it is implemented as a double linked list. Okay. Now, if I am going to, now let us do one more way, that I can also maintain a binary search tree as a simple linear array. Now, if I am going to do like that, I maintain a linear array like this. Where this will be 1, 2, now I can also maintain it as a linear array, where the root element will occupy the first position, and the left child will occupy the position of 2 into I, where I is the index of the parent, and the right child will occupy the position of 2 into I plus 1. Now here the index starts with 1, because if you take the index as 0, 2 into 0 will become 0. Therefore, I start the index from 1 and the left child of this will be stored at 2 into I is 2 into 1 is 2. Therefore, you are going to put the left child over here and the right child over here. Similarly, to put 70, you find the index of 80. Index of 80 is 2. Therefore, 2 into 2 is 4. Therefore, 70 will occupy this position. Now, in order to store 120, you check the index of 150, it is 3. Therefore, 3 into 2 is 6. Therefore, 120 will come here. Similarly, 2 into 2 is, therefore, now index of I is 3. Index of 150 is 3. Therefore, 3 into 2 is 6 plus 7. Therefore, 170 will come here. Now, 200 will come to the position number 7 multiplied by 2 plus 1, because position of 170 is 7. Therefore, you replace over here 2 into 7 plus 1, it is 15. That means you will store at this position.
Yes, sir, will you repeat it from 150?
Pardon?
Will you repeat from 150, sir?
See, 150 I am putting because 150 is the right child of 100. Now, the position of I for 100 is 1. Now, this is I. Now, 100, that means I am going to put 150. That is 2 into I is 2 into 1 is 2 plus 1 is 3. Therefore, 150 will come into 3. Now, I is the index here. I is the index of parent. Now, in that case, when I want to put 200, the parent of 200 is 170. The index of 170 is 7. Therefore, since it's a right child, it will be 2 into 7 plus 1 is 15. Therefore, you will put 200 at 15 position. And rest of the things what you find will be blank. Now, in that case, if I had a right child of 200, what is the index position you want to store that child at?
31.
Of course, it will be 31. That means from 16 to 30, you will have blank spaces. And therefore, if I am going to have a right child over here, which might be say 250, you will store it at the position of 31. Now, just check. There are 31 spaces which are being used. And obviously, how many of them contain data? Only 8 of them. Only 8 contains data. Because there are only 8 nodes. That means out of 31, you are having only 8 nodes which are 8 spaces which are occupied. That means occupancy is hardly 25%. It's 25%. In the worst case, if you are having another node at the right of 250, it will come to the position number 63. Therefore, if you put a number at 63rd position, all the spaces from 32 to 62 will be vacant, or will be blanks. Since it's an array, you cannot reclaim those spaces because obviously the array is static and you cannot reclaim those spaces. Now, therefore, you can say that array is not the best representation to store an entry, but it is possible to do that. Now, if I just take this array and try to reconstruct the tree, it is too easy. What you do is that, what you can do is that what I can do, I will just remove all this. And I can reconstruct the tree. Now I will take the first position 100 and make this as a 100. Then I want to know where is the position of 80. What I will do, I'll divide by 2. The index of I is 2. If I divide 2 by 2, that means 80 index is 2. Therefore, I'll divide by 2. I will get 1. If it does not give a remainder, it means it's a left child. That means this will be 80. Now I will take for 3. It will be 3 by 2. Will give you 1 with a remainder 1. It means that it's the right child of index number 1. Right child of index number 1. Therefore, in that case, this will be 150. Again, I will take this 4. I will take this 4. 4 divided by 2 is 2. With a remainder 0. It means this is a left child of index number 2, that is 80. Therefore, it means that it's a left child of 2. That means it is 70. Similarly, I will take for this 6 divided by 2 is equal to 3. Therefore, it is the left child of index position 3. That is 150. And that means 120 will come here. Now we'll take this for this one. It is 7 divided by 2, 3, with a remainder 1. If the remainder is coming, it's the right child of index position 3, which is 150. Therefore, this will come over here. And similarly, if you take for 15, it will be 15 divided by 2. Will give you 7, with a remainder 1. Now check the 7th position, it is 170. Therefore, it is the right child of 170. And similarly, 250 you will put at the right child of, because it will be nothing but 31 divided by 2 is 15. Since it gives a remainder 1, it is a right child of 200. And you can reconstruct the tree from this array. Now you should very well have known by this time that you are not going to store the tree in the memory. You are going to store the representation of a tree, which can be an array or which can be a linked list. If it is a linked list, obviously you can save space. But of course, when you save a space, you are saving a space at the cost of 2 pointer values. Because this, when you are going to store like this, you are going to have a particular like this. This value is going to be stored from here, and this is going to be stored from here. Obviously, the node will take how many bytes? Suppose 100 takes 4 bytes. 2 pointers will also take 4 bytes. Therefore, approximately, this will take 12 bytes each. Now, but you are only storing 8 nodes. Therefore, the total tree will take only 96 bytes. 12 into 8. Whereas, here it will take 31 into 4, 124 bytes. Though this will only take 4 bytes, this is only 4 bytes each. Total will take 31 into 4 is 124 bytes. But the bigger problem is that the moment you want to add a node in this tree, you cannot grow the size of the array, because you will declare the arrow before you are going to make a tree. That means you have to declare the array of reasonably big size so that you can be very sure that whatever nodes are going to come, you are going to put into this array. That means if I am not sure, I will declare an array of 1000, maybe 2000. because I do not know how many nodes I will require. Now just take a simple example over here. If I have a tree like this, how many bytes required? First position, second, fourth, sorry. First position, third, seventh, 15, 31, 63, then 127. And if you put one over here, it is 255. That means to just store 8 elements, you require 255 elements. And you put one more, it requires 513 elements, 13 spaces. That means you have to declare an array of, let us take it from 1 to suppose 2000. You will be able to just, you will be able to just put how many elements? In the worst case, 255 into 2, 510 approximately. Then one more, 1000, then 2000. That means with only 10 elements, you will occupy the whole 2000 spaces, because you will, the next element after this will be 511. After that it will be 1023, and the next element will be 2047. That means you can only store 10 elements. Now just check it out. 1, 2, 3, 4, 5. Then this you cannot store because you are only having 2000 spaces. That means the occupancy will be only 10 divided by 2000 space. This is percent. This is the array occupancy. Okay, this was percentage. And if you are going to just let us calculate by this. That is no, sorry. This one here is fine. They 1 by 200. 0.0005. No, that is the worst case. But if the array is a complete binary tree, obviously there will be no spaces which will be vacant. Now let us try to get this concept. If I am having a tree like this, now this is a complete binary tree. Now you check it out. The element will be stored at first position, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. And you just require an array of an array of 16 elements to store these 16 elements, because there will be no spaces which will be vacant. Then in that case, this implementation is very good. But again, I will tell you, this will only work if you are doing it programmatically. You cannot declare an array of 16 just because you are not sure how many elements I am going to insert. Therefore, I cannot make a C declaration like this. For example, say I can say A of 16 and can work upon this, because this is a case where it will only work for this case. But I cannot say beforehand how many nodes are being inserted. Of course, if you know that only 20 elements will come, you might be able to put that way. Therefore, even if the array implementation is not good, even if if the tree is a binary search tree, because practically it will not sustain, because initially I cannot know how many elements you are going to generate. In most of the problems in the real world, you do not know how many elements are there. Of course, in some problems I might know. For example, suppose in the class there are 122 of you. I might say 110 will come. I might have it as that route. I might have such ways. But in in most of the places, I cannot do, because I'm not very sure how many. I cannot have a typical guess to find out how many people or how many elements will be there. Therefore, what I'm trying to say, that array representation is obviously one of the possibilities, but practically we should try to do it using a linked list, because in that case it is much easier for you to do. Though insertion in an array is much easier, because you just keep on trying to find the appropriate position by just multiplying 2 into I or 2 into I plus 1 and keep on doing. Okay. Now, just suppose I am going to write an algorithm for this. Now, just how to insert. Now, already I have given in the last class. Just I will try to show you how it works. You already, when the first element will come, I will be putting it as a root over here. Suppose the first element is 100. Now the second element, what is going to come, you compare with this. If it is less, you follow the left pointer. If it is more, you follow the right pointer. That means it is basically going to be like this. It will be something like this. Okay, this is the first node. Now second node, suppose I am getting a number like this: 100, 50, 130, 65, 200, 110, 20. Suppose I want to insert these 6 elements. Now the first element is 100. I make it a root and have a pointer over here with the root. Then the second element is 50. I have to compare, but I cannot shift the root. Therefore, what I am going to do, I'll make one more pointer, which is nothing but 10. And then I compare 50 with 100. Since 50 is less than 100 and the left is free, I will bring one node at this place, which is 50, and connect it like this. And make this as null, make this as a null. And obviously, this is null. Okay. Now again, 130. I compare with 100. It is bigger than 130. Therefore, the temp will not come in the picture, because you can directly insert at the root. Now, what I will bring? I will bring this node 130 over here, and we'll just connect by this, and make this null, make this null. Then I get 65. Again, I compare with 100. Now it is less than 65, but I cannot insert over there because that space is already filled. Therefore, now what I do, I write temp is equal to temp of left, and now temp will come here. Or temp will come there. Now again compare 50 with 65. Now you know 65 is bigger than 50. Now I check the right link. Right link is blank. Then what I do? I bring the I put the 65 over here and connect it like this. And put it like this. And again, this temp will again go back to this place. Then again compare with 200. Now 200 is bigger than 100. Now you follow the 10 in the right link, and 10 will now come here over here. Now you find that right of 130 is free because 200 is bigger than 130. Therefore, you bring 200 over here and just going to put like this. Then again with 110, similarly you have to move back 10 to this place, and again 10 will now come here. Every time you are going to root, temp is equal to root. And again with 110, you compare with it's bigger than 100. Now temp will again come back to this place. Again temp will again come back to this place. And you know that 110 is smaller than 130. Therefore, you will make a 110 over here. And with this one, you are going to like this. Similarly, with 20, you will know that 20 is smaller. You will put over here. Now, if I want to put one more element, for example, I might put say 10. What I will do, I again start from here. I will again start from here. I compare 20 with 100, it's smaller. Now in that case, 10 will now shift over here. Again I compare with 10 is less than 50. I again shift 10 to the temp of left. Now again compare 20 with 10. 10 is smaller. Therefore you make a node at this place. And just select like this. And then now again temp goes back to original position. Now this is how you are going to do. Now in that case, how much you have to traverse to the height of the tree. Maximum you have to traverse to the height of the tree. And this is a simple algorithm you can very well write. Okay, just you have to make sure that you reach to the position where either the left or the right is free. Correspondingly, you have to put the node either onto a node when this is the case. Now, for the equal case, what you are asking, normally when you are going to perform, you are going to make a binary search tree with equal elements, it is normally not there. Why we do not consider the equal cases as asked by one of your friend Vital Gulati. Now see, actually when you are going to do it for unique elements, equal normally will not come. For example, you are going to search for roll number of the students, there will be no equal. Or I am going to search a particular element in a bank or account number, there will be no duplicates. Now, why they did not take equal cases? Because when you are going to perform a search, duplicacy will not come. But in some particular problem where you find that there are duplicates, you have to either make some at left or right, you have to take equal to also. Now, when you are going to search a duplicate value, in that case you cannot find the index position. Now, let us take an example. Suppose I have one element over here which is having another 10 over here, somewhere over here. And I want to search 10. Now, if I want to compare 10, obviously, I will not be able to put this 10 over here. But if I am going to find an array also, we will end up in getting either this one, or this one. There are two 10. Now, obviously, you cannot be sure which 10 you are going to search. Therefore, when we talk about this unique elements, duplicacy is not there, because when I'm going to search a number, I can search you by your roll number and not by your name. Okay, there are more than one person with the same name in your class. Therefore, if I call you by name, obviously both of you will answer. But if I call you with a roll number, only one of you will be there. Therefore, we can safely assume that when we are making a binary search tree, a duplicacy will not be there. But if a duplicacy exists, you can always try to put it either in the left or the right branch, depending on your consideration. For example, I might say that left should be less than or equal to root, and right should be bigger than root. Now, when I am going to put this one equal to, I am only putting it a very special case. But in a practical scenario, you will find that duplicacy does not exist in these cases. Therefore, if you see all the standard books, they don't talk about duplicates, because searching with a duplicate number is always is wrong, because you cannot get that actual value. For example, if I call a person with your name, there could be two people, and how will you know whom I am calling? Okay, because that's the problem. Now let us see, this is an insertion case. Now let us see how to do a deletion. Now let us try to make a suppose the tree will like this. Let us put some numbers. Okay. Now this is a binary search tree, because obviously the criteria holds that the root is bigger than the left and smaller than the right at all levels. Now let's try to delete a node. Now if you are going to delete, there will be three cases. There will be three cases. The case one is the node is a leaf node. Second, node has one child, exactly one child. And case three, node has two children. Now these cases has to be handled differently. Now already you know that when I am going to make a tree, obviously the only thing what you are having at this is the root. Now I am trying to tell you time and again that the only thing which is at our disposal is the address of the root. Nothing more than that. You can only come from root to the other nodes by following the links. Now, when you are going to perform a deletion, let us try to take, I want to delete 120. For example, with a case 1, I want to delete 120. Now, first of all, what you will do is that to find the position. Now, as I have been telling you again and again, you start with a variable temp. You compare 120 with 100. It is bigger than 120. Then temp will point over here. Again, you compare 120 with 140. It is smaller. Therefore, you will point, temp will now come here. Then you again compare 130 with 120. It is again smaller. Temp will come here. And now you have found the node to delete. And to delete 120. To delete 120, what you will do is that you have to put a null in the left of the 130. Now 130 is somewhere like this. Now you have to give an address over here and there is an address over here. This address of 120 and this contains address of 130. Fine. What you do is that you have to put a null value at this position. And you have to go back. So you have to go back from 120 to 130. But you can't go back because the links are only from the top to bottom. That is from the parent to the child. There is no link from child to parent. Therefore, from 120, I cannot go back to 130 because I don't have backlinks, because not a threaded tree. It's always a one-way link. Therefore, you cannot perform deletion by this method. Now, what should be the way out? What should be the way out? What should be the primitive way out, which I have already discussed in many problems? You start with 2 pointers. One pointer called temp1 and one pointer called temp2. Make sure that temp1 is pointing to the child, temp2 is pointing to the parent. Therefore, when temp1 will come here, temp2 will remain here only. When temp1 is going to come here, temp2 will point to this place. Similarly, when temp1 will come here, temp2 will point here only. And then you find that 120 is to be deleted. Now it's as simple as that. You write temp2 of left is equal to null. What you do is that you write temp2 of left of temp2 is equal to null. And that means this is now gone. Of course, less than elements are in the left of the row of the child. Now, second case is the case 2, where you have to delete, let us say, delete 160, which has one child. Now, in that case, again, you start the same thing. You start from the top and you are going to delete like this. Therefore, what I can do, I start again from here. Okay, I just start from here. Now I take temp1 and also I take temp2. Then I will reach to this place where temp 1 will point to this place and temp 2 will point to this place. Okay. Now I will delete 160. Now what does 160 right contains? The address of 180. Now in that case, it will be something like this. Something like this. This contains null and this contains address of 180. Now what you do is that you pick that address of 180 and you put it into the right of 140. That means you write one statement over here. What you are going to write? You are going to write like this. You can write like, now you can put, that means you might write temp 2 of right is equal to temp 2 of right is equal to temp 1 of right. What will happen? It will copy the address 180, and now this one, what will happen? That this will now point to this place. Because this one will be now copied and will put into the right of 140 bar after you write this statement. And then what you do is that this 160 is now no more connected, and you write free temp 1. Now you just write free temp 1 and that will happen. This will now go. And your deletion is done. Okay. Now the case 3. In the case 3, what is happening? That means you are going to delete. The case 3 is little tricky. Where suppose I want to delete 80. Now 80 is having 2 children, or 140, or I can delete 100 also, or 130 also. Any node which are having 2 children, 100, 80, 140, 130 are having 2 children. Now here, how will you do? Now this has to be very, very understood very perfectly. Now what you can do is that when you are going to delete like this, you have to perform an in-order traversal of the binary tree. Now what I will do is that I will be doing now delete now what I can do is that for this one I perform the in-order traversal. Now you check the in-order traversal. What is the in-order traversal? You do in-order traversal for this. In-order traversal means left, root, and right. Now what is the in-order traversal? 55, 50, 70, then 80, 85, 100. Now let me write the in-order traversal for this. Eighty, 85, 100. Then it will contain 120, 130, 135. then 140, 180. Okay. Now this is the in-order traversal for this binary tree because left is null, 50, 55, 70, 80, 85, 100, then 120, 130, 135, 140 and 180. Assuming that 160 is not there. Okay. Now, what did you notice over here? What did you notice in this? Anything you notice? Yeah, I want an answer because you can very well see the trend and can tell me. It is all good. It's all sorted. That means whenever you are performing an in-order traversal of a binary search tree, it always gives a sorted order. And this is a sorted order. The in-order traversal of a binary search tree always gives a sorted order. And that is a very important thing, that without traversing also, if you have written that in a sorted order, the answer is automatically comes. But I don't tell you that you try to do like that, but it is perfectly valid. That means all these elements which are given, you just sort it manually and it will give you that. Now, the question was, what was there? You have to delete 80. That means I was to delete, you have to delete 80.
Excuse me, sir.
Yeah.
I need to get lunch, sir.
You want to?
Get lunch.
Okay, just 5 minutes, or you can, I will finish in 5 minutes.
Okay, sir.
Now you want to delete 80. Now, in order to delete 80, what you have to do is that you have to check the in-order successor for 80. You have to check the in-order successor for 80. That means the in-order successor is this one. And this is the in-order and you find that 85 is the in-order successor. Now what you do is that once you find that 85 is the in-order successor, you have to do two things. If 85 is a leaf, you delete using case 1. If 85 is not a leaf, delete using case 2. That means you have to do 2 steps. 1, if 85 is a leaf, to delete that node 85 using case 1. Otherwise, 85 is not a leaf. It will always have the only right child. Now, one thing observation is to be very, very clear that the in-order successor will not have a left child. The in-order successor for 80 cannot have a left child. That means this thing, maybe I put say 82, it is not possible that 85 will having a left child. 85 might be having a right child. Why I say this? Because if 82 would exist, the in-order successor for 80 would have been 82 and not 85. That means this is not possible. The only thing is that 85 might have a right child, which is true, which is possible. In that case, you delete that node with case 2. And then once you delete that node, don't discard it. And what you are going to do is that just replace this node with this. Just replace that node 85 with 80. And you find that the property of binary search tree is maintained. And now what you have to do is that you have to do 2 things. 1, delete 85 by case 1 or case 2, and then replace the deleted node with 80. That means you will note, and I just take it as a very, very important observation, that the in order successor for that node will never have a left child. And therefore, if 85 will have a child, it will always be a right child. And by this method, you can delete a node with this. Now, similarly, if I would have needed to delete 100, if I need to delete 100, what I will do? I will check the right. I will check this, that this is the. Therefore, I will delete 180 over here. Now, in that case, you have to delete 120. Now, you check 120 is a leaf. And then you delete 120, and just to delete 120 like this, and replace this as with 120. And the property of binary search tree is maintained. Now suppose now you have to delete 120. Now you have to delete 120. Now what you do? You perform a in order successor. Now 120, after 120, 130 will come. Now you have to delete 130. To delete 130, you have to delete using case 2. What you do is that you have to replace the left child of left link of 140 with 135. That means you have to perform like this, or you have to maintain like this. And then you delete 120 and replace with 130. And this is how it works.
Sir, attendance.
Just a moment.